All right, so now we're going to start looking at simplifying these radicals expressions. Now, first, let me just define a word for you real quick. Radicand. When I refer to the radicand, that's just a better way of saying the part that's underneath the radical. So, if I gave you, like some of these radicals, square root of 14, right? 14 is the radicand because it's under the radical. Square root of L squared plus W squared. That's, again, L squared plus W squared is the radicand. 2GD, the radicand. In this fourth one, D is the radicand. 4 is not really inside the radical. D is really the only thing that's inside the radical, so D is the radicand. 2 is the radicand here. 5 is not, because 2 is the only thing that's inside the radical. So radicand just means, the piece of the function, equation, expression, whatever, that's inside your radical. So there are three big, rules for radicals and being in simplest form. So rule number one, and the big one that we'll work on a lot in this video, is the radicand has no perfect square factors. So basically that means that you can't divide it by a perfect square. And you're going to want to know your perfect squares really, really well. So we'll list them probably again and again in this video, but if you want to take a piece of paper and write them down, I certainly encourage that. I'll go ahead and list a few out here. So, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, 10 squared is 100. These are probably the biggest ones that we'll have to get to. But we'll add to this list if we need to. But these are perfect squares. So basically, we're going to see if any of these numbers divide into the numbers that we're getting from our expressions. So rule number 2, the radicand has no fractions. That just means that, so for instance, square root of 1/2, that's not simplified because you can't allow a fraction to be within inside your radical. It's a pretty simple way to fix this, but sometimes it leads to this third rule being broken, which is one that we'll also have to be very, very careful about, and that's there's no square roots in the denominator. So we'll look at all those, but we'll focus our attention a lot on number 1. So know these properties about radicals, okay? So the square root of a times b is the same as the square root of a times square root of b. So basically, those two parts can be broken up and it still equals the same thing. And you could try this with your calculator too. But they do a good job here with the square root of 100. So the square root of 100 is the same as the square root of 4 times 25, because 4 times 25 is 100. So, and the square root of 4 times the square root of 25 is the same thing as well, where you can split them up. Now, square root of 4 is 2, square root of 25 is 5, and so that answer is 10. But the square root of 100, of course, was 10. So you can see that no matter kind of how it's broken up, it still equates the same thing. So it's an important rule that we're going to make note of. All right. Same thing works with fractions. So we've kind of talked about this being, I think, the second rule that we listed out of the 3 earlier. But we can't have we can't have fractions inside the radical. And the good thing is, if you have a fraction inside the radical, they split up just like the multiplying split up. So when you have something like the square root of 36 over 4, that's the same as the square root of 36 separately and the square root of 4 separately, kind of in their own respective parts of the fraction, the top and the bottom. And you can see this all equals the same thing. This ends up being square root of 9, which is 3. And of course, this ends up being 6 over 2, which is the same thing as 3. So it's not, this is just proof, well, kind of proof that it works. But yeah, just remember the rule basically that if you have something times something in a radical, you can split up those two things into their own separate radicals. And the same thing works for division. If you have something dividing by something inside a radical, you can split up those two things into their own individual radicals. So we'll be using this property a lot when we're simplifying. All right, so let's try simplifying the square root of 24. Now here's the thing about the square root of 24 is it's not a perfect square. Remember the list that we made earlier? Hopefully you wrote it down. These perfect squares, obviously if you ever had them inside the radical, they simplify nicely, right? Because, I mean, that's why they're called perfect squares, right? 24 is not a perfect square. In fact, if you try to type this in the calculator, you get a decimal value, but that's not our goal. Our goal is not to just write this as a decimal value. Our goal is to write it as a radical, but a simplified radical. So it's kind of like simplifying fractions, except we're not trying to reduce just by any number, but we're trying to reduce by perfect squares. So when you look at 24, you think about what perfect square, so which one of these numbers here divides into 24? Which one of those is a factor of 24? 4, 9, 16, 25. Well, it's not going to be anything bigger than 25, of course, because those numbers are bigger than 24. So 4, 9, 16 are really only options. And we want to choose the biggest one. It's kind of weird, but unfortunately, the biggest one is 4. 4 goes into 24, right? 4 times 6 makes 24. So keep in mind that what I've just written here is the same thing. 4 times 6 is 24. It still equals the square root of 24. But now we're going to use that rule that we talked about earlier where we have these two pieces inside the radical that we can separate them into their own, right? So this is the same as the square root of 4 times the square root of 6. So separating them out. Now the reason we chose perfect square is because the square root of 4 is a perfect square and it's going to simplify very, very nicely, right? The square root of 4 is 2. Now the square root of 6, of course, is not a perfect square. And none of these numbers up here will divide into that. So it's left as the square root of 6. And there's nothing we could do to change it. But the square root of 24 simplifies to 2 times the square root of 6. So, well, again, the whole process is find a perfect square that divides into this, separate them out, take the square root of the perfect square, and then leave that extra piece as your remainder. You can't really change anything. You can't really do anything about it. As long as it's, still not divisible by any of these other perfect squares, then there's nothing we can do. We kind of leave it as sort of a quote-unquote remainder. All right, but that's kind of how it works. So let's try a couple more and see if we get the hang of it. So I'll do this one in a second, but I kind of want to keep our attention on the numbers for a moment. So let me just kind of make one up. Let's do the square root of... What should I try here? Let's do... Man, it's hard thinking. Let's just do 40, why not? All right, so 40 is not a perfect square. We know that. But our goal is to think of, a perfect square that divides into 40. So remember, perfect squares 4, 9, 16, 25, etc., etc. Which of these will divide into 40? The biggest one, preferably. In that case, it's 4 again, right? 40 is the same as 4 times 10. All right, so 4 is the number we chose that will divide into 40. 10 is, of course, what makes it, multiplies with the 4 to equal 40. So you separate those out, square root of 4 times the square root of 10. And we can simplify each individual piece. The square root of 4 simplifies to 2. Square root of 10 doesn't simplify anymore. Square root of 10 is just left. That's the square root of 10. And that's the same but simplified version of the square root of 40. If you want to take your calculator and type that in, you're going to get a decimal. But if you type this in, it's the same exact decimal because, of course, they'll be equal to each other. But this is a simplified radical. The square root of 40 was not. All right, so let's go ahead and let's look at the ones with the variables here. So here's the thing about variables like this with exponents. If it has an even number exponent, it's a perfect square. So to explain why, x times x, is x squared. X squared times itself is x to the fourth. X to the third times itself is x to the sixth. X to the fourth times itself is x to the eighth. And this pattern continues. X to the fifth times itself is x to the 10th. So it's a perfect square if it has an even number exponent. So this is going to be pretty easy so when I see the square root of x to the fourth, I immediately know that it's just essentially half that, right? And it'll be x to the second, as you can kind of see illustrated here. So if I had x to the 20th, right, square root of x to the 20th, I know it's going to be half that, right? Square root of x to the 20th is simply x to the 10th. So any even number is going to be really easy to work with. It's the odd numbers that take a little bit more, but not too much more. So let's look at this one, and let's use that rule where we can separate these two out. So the square root of x to the third. Oop, I'm in a bad color here. Let's use red. Okay. So separate these out. Square root of x to the third times the square root of y to the fourth. Give me 1 second. Allergies are getting me hard, man. All right, so and we'll simplify these individual pieces. Now the y to the fourth, I'll just do that first because it's an even exponent. It's going to be pretty easy. The square root of y to the fourth, I'll just do it over here on the side, is y to the second, plain and simple. So I'm going to put that back in the problem in a moment. But let me simplify the x to the third part. So this is a little bit different. So how odd numbers work is what you're going to do is just basically take the biggest even number that's before your odd number. So in this case, x to the third, the number right before it, even number right before it is 2, right? 3, the biggest even number before 3 is 2. And separate that from that odd x. So this is del x to the third, right? X squared times x. It's still technically x to the third. But what I've done is I've chosen the biggest perfect square. Like I said, any even number exponent is a perfect square. So when I simplify this, I kind of treat it the same way I do with the numbers, where I can separate them out and then start simplifying each of them individually. So square root of x squared is plain and simple x, where the square root of x, however, not so lucky, stays underneath that radical. So this is how we simplify our odd numbered exponents. Now let me just go ahead and write the answer here, and I'll explain a little bit more about these odd number exponents. So my answer, x to the third, square root of x to the third simplifies to x, square root of x. Y to the fourth simplifies to y to the second. So a better way to write this answer is simply x, y to the second, square root of x. You always want to write the radical part last. Anything that's not inside a radical should be written in front of the radical. So I simply kind of just move this y in front of the radical just to make it look a little bit cleaner. All right, but let's talk about these odd number exponents again. So if I take, let's say, a to the 11th power, right? Odd number exponents are not perfect. So what we're going to do, and what we always do, is just take the biggest even number that's right before it. So in this case, 10, right? A to the 10th, and then that 11th a will be kind of split to the side. And we square root these individually. I'm good, thank you. Square these pieces individually. Square root of a to the 10th is a to the 5th, because remember, any even number, you just take half of it. And the square root of a is left as kind of that leftover bit. So every time you have an odd number exponent, you're going to have sort of this extra variable in the radical. It should always just be that variable. plain and simple. So just one more, and we'll do kind of an exotic one. But let's say I had b to the 51 power, 51st power, right? The biggest even number before 51 would be 50, so it'd be b to the 50, and then that 51st b. Notice I kind of went ahead and skipped a step here. I just went ahead and separated out those two terms. So it's b to the 50 being an even number. We just take half of it. So this would be b to the 25. And then the square root of b is the square root of b. So that's going to be it. That would be the answer to that. And what a lot of people do, and they do this by mistake, is they put a square, after they simplify the radical, they keep the radical there. And now that's a mistake. You don't want to be doing that. Once you've done the square root, once you've simplified a square root, it's gone. You don't have to worry about that anymore. So b to the 25th power, a to the 5th power, those things are no longer in the square roots because you've already done that square root. So it's free, be on its own. You don't have to worry about it. All right, let's move a little bit ahead here. So this one's got a combination of numbers and variables, but it's treated almost exactly the same as everything else. So just break pieces apart individually and just deal with them individually. So we'll deal with the square root of 48, then we'll deal with the square root of a squared, then we'll deal with the square root of b. So because, again, these are all being multiplied together on the inside here, we can separate them all out. Now, if there was any plus signs between them, this wouldn't work. But as long as they're all bunched together, it will. So let's deal with these one at a time. Square root of 48. Remember, for numbers, you have to try to find the biggest perfect square that goes into them. So for 48, I believe 16 is the biggest perfect square that divides into 48. 16 times 3 makes 48. So separate these two numbers. Square root of 16 times square root of 3. Square root of 16 is perfect square. That simplifies to 4. Square root of 3, not so lucky. It's left as the square root of 3. But there's your simplified version of square root of 48. As far as square root of a squared goes, this is pretty simple. Because it's an even number, you just take half of it. So it's really just plain and simple a. Square root of b is an odd exponent, but it's just the square root of b. I mean, the biggest even number would be 0, so you can't really do anything with it. That's kind of a lost cause, but it doesn't really simplify. It remains the square root of b. So my answer in these three parts, let's just put them all together. So remember, anything that's outside the radical should be written first. So 4 and a are outside the radicals. And then you have the square root of 3 and then the square root of b. Just to clean this up, if anything that's under the radical can go into the same radical. So we can write this, instead of writing square root of 3 and square root of b, we can just write square root of 3b and leave it like that. Okay, so that is simplifying radicals, basically. If there's a couple examples, I'll rush through them kind of quickly. Let's do a couple of these actually, because they've got the fraction part. All right, but they're treated the same way, but we separate them instead of side by side. They're just on top of each other. So remember that this would separate. The 5 would be in its own radical. The 4 would be in its own radical, and we would simplify each part individually. Now, square root of 5. 5 is not divisible by any of these perfect squares. So square root of 5, kind of a lost cause, doesn't really simplify. We leave it like that. The square root of 4, however, is 2. So we can simplify that to 2. And that is our simplified version of that problem. So with b, here's a special thing to consider. Consider simplifying the fraction first before doing anything with the square root. So if there are 3 m's on top and an m on the bottom, then this, just to kind of emphasize a point here, that 1m on the bottom will cancel with one of those on the top. So really, let's rewrite this as square root of m squared over 9, where this m and 1m from the top canceled out, leaving you with m squared. This is better because now it's a little bit easier to simplify when we separate these out. Square root of m squared and the square root of 9. Both of these are perfect squares, and they work out really, really nicely. So square root of m squared will just become m, because you just take half that exponent. 2, half of 2 is 1, so m to the first power. And square root of 9 is 3. So it's just going to be m to the third. So be on the lookout for that. If you can simplify the fraction first, go ahead and do that. It'll save you plenty of heartache. All right, and then we'll try this last one here. It's a zesty little example. So this doesn't, none of this in here simplifies, so I'll just go ahead and start breaking it apart. So square root of z to the fifth on top, square root of 25 on the bottom, and square root of y squared also on the bottom. So everything just basically gets its own little radical, right? And then I'll start simplifying each part of these individually. So I'm going to pull it off to the side here so I don't kind of get in the way. But z to the fifth, so z to the fifth is an odd exponent. So remember, you have to take the biggest even number before 5. That would be 4, right? Z to the fourth, and then that fifth z is extra, kind of chucked to the side. So the square root of z to the fourth will be z to the second, and then the square root of z that was chucked to the side kind of hangs around. So that's a simplified version of z to the fifth. That's going to go on top. So we'll have z to the second, square root of z. On the bottom, well, I think these are pretty straightforward. Square root of 25 is 5, and the square root of y squared is y. So I don't really have to pull them off to the side to do them because they're both perfect squares. They both work perfectly well. So my answer is that right there. Don't know if they're going to have it. There they go. All right. Just this one real quick, I guess. Square root of p to the sixth, square root of q to the 10th. Both of these are perfect squares. Half of 6 is 3, so we get p to the third. And half of 10 is 5. You get q. I don't know why it keeps doing that. Q to the fifth. I don't understand. Anyway, so that would be the simplified version of that. All right, so next time we'll add, subtract like radicals. Sorry if this video kept it kind of long, but I'd like to be kind of thorough. So I'll see you guys in the next one. Bye.